Concentration of solutions. We're basically going to be going over 5 separate equations or way to calculate concentration. First one is, and actually the first 3 are all percentage calculations. They're done the same way any other percentage calculation would be done. We're going to take the portion and we're going to divide by the whole and multiply by 100 to express it as a percentage. The first 3 will be very similar except for in the way that they're being used, the units being used, and the sort of situation you're being used. So this one here is a mass volume percent. So anytime you have a solution where you're taking a solute that's generally a solid, you'd probably be weighing it in mass units and most likely grams, and then you'd be taking the solution that you're going to be making up that would be measured in milliliters. So we're using those 2 units, the mass of the solute in grams divided by the volume of the solution in milliliters, the whole entire solution in milliliters. Multiply that by 100 and you have a percentage. So for example, if you had a bottle of Mountain Dew and in it, if there were 13 grams of sugar for every 100 milliliters of the soda, what is the mass volume percent of the sugar in this bottle of pop? Easy calculation, mass 13 grams divided by 100 milliliters. Now this is grams divided by milliliters, so technically the units don't really cancel out, but we're imagining that we're dealing with a portion of a whole. The grams would then be in the milliliters, so we are canceling them out, and we are ending up as a percentage. So this is just a mass volume percent, often used when you're dissolving a solid into a solution. Second one, very similar, except for it is a mass percent. Both the solute itself and the solution are going to be weighed in grams. One of the common places you'd see this would be in something like a solid solution, like a metal alloy, where you have 2 different metals that when they're hot enough they would be liquid, but then they'd cool and form a solid. So you may be weighing them while they are in their solid form, and therefore it'd be convenient to use mass in grams. So for example, let's say you had a ring and it weighed 24 grams and it was made using 18 grams of gold, and the rest, the difference, would be made up of other metals that would give the gold maybe more strength and make it a lot cheaper to make. So anyways, 18 grams of gold in a 24 gram ring. What is the percent gold in the ring? And this is a mass calculation. Very simple again. You take the portion that is gold and you divide by the whole that is the ring in which the gold is in. In this case, the units do nicely cancel out, and we do still end up with a portion expressed as a percentage. So 18 divided by 24 times 100, this ring would be 75% gold, 25% other metals. Last way of calculating concentrations in a percent calculation would be volume. And this might be a case where the 2 things that you're using are both liquids. So say you had maybe an acid that was being added to water, or alcohol to water, something like that. You'd be measuring them most conveniently in milliliters. So if you wanted to express the concentration of the solution, it would probably be in a volume percentage. Same idea as the last 2. You take the volume of the solute, the portion, and you divide by the volume of the entire solution. Multiply that by 100 and we have it as a percentage. So if a 4-liter bottle of vinegar has 200 milliliters of acetic acid in it, what is the volume percentage of vinegar? Both these are milliliters. They're going to, sorry, this one's milliliters, this is in liters. You can convert that in your head if you like, if you want to work it out mathematically. Again, the goal would be to use conversion factors. So we'd take our number that we want to convert, we would multiply by something that would get rid of the unit we want to get rid of, liters, and we want to convert this to milliliters so that we can have the acetic acid and the solution in milliliters. And then we write the numbers, and we know that 1 liter contains 1,000 milliliters. So when the liters cancel out, we'll be left with units of milliliters. So 4 liters must be 4,000, 4 times 1,000 milliliters. And proper sig digs for this, I'm going with 2, so really I should write this as 4.0 times 10 to the 3 milliliters to get the proper sig digs. You can do that in your head or use a conversion factor. Either way, we're doing 200 milliliters. That is the acid that is in the 400 milliliters of solution, and we multiply by 100 to express it as a percentage. Volume, volume, percent. The fourth type, a little bit different. You've seen this one probably on water bottles. If you look at the ingredients of a water bottle, often a lot of the ions that are found in water are found in very, very small concentrations. So they tend to measure them in things like ppm, which stands for parts per million, or if they're really, really small, it might be parts per billion. So if you had a million molecules out of this bottle of water here, magnesium would make up 2 of those parts. So there'd be a million molecules, and in there would be 2 magnesium, and we know this is not metallic magnesium, this is an ion, so there'd be 2 positive magnesium cations for every million things that there are in this, million particles there are in this water bottle. So this is another way of measuring concentration, how many of a certain type of particle are in every million particles that you're dealing with, or billion if that happens to be the case. To do this calculation, to find the parts per million, you need to find out what it is that you're talking about, so the solute itself. So we talked about magnesium, maybe that's the one you're talking about. And then you take the solution, and you'd want to have the same units for each. So you'd find the mass of the solute, and you divide by mass of the solution. And obviously that would give you a very small number if there's very little of it there, because the solute, the numerator here would be very small, and the denominator, the solution, would be quite big. So to express that in a more workable number, we multiply it by its parts per million, we multiply it by a million. If it's even smaller, we can multiply it by a billion, and that'll tell us how many parts or particles of the solute there are per every billion parts of the solution. Now, either one of these equations, as long as you have 2 of the variables, so if you have the mass of the solute, mass solution, you can multiply take the mass of the solute, divide by the mass of the solution, multiply by 1 million, and you'd get parts per million. But if you wanted to find mass of the solute, if you already had parts per million and you had mass of the solution, just rearrange this equation for mass of the solute. Just like any other equation, you can easily rearrange it through algebra. Now, the one thing with these is make sure that both your solute and your solution are in the same units. So if one's in grams and the other one's in kilograms, or one's in micrograms and the other one's in milligrams, they have to be converted to the same unit before you can use this equation or the parts per million equation. Alright, those are all good for common usage, things like water bottles and vinegar bottles and gold alloys and that sort of thing. But as chemists, we really are concerned about the particles. Now, if we're talking about particles, we want to talk about them in a manageable way, and the only way to do that is with the mole. So obviously molar concentration will be the most important of these 5 calculations, because it allows us to talk about moles, then we can get into equations and work from there. So the molar concentration is expressed in how many moles there are for every liter of solution you're dealing with. So find out what the solute is, and find out how many moles you have, and then divide by the entire volume of the solution expressed in liters. So molar concentration, always moles per liter. The equation we have for this, we just say that the concentration, same equation we have up here, the molar concentration, we use a capital C for that, that is equal to the number of moles, which just like before we use a lowercase n, divided by the volume, capital V. So there's our equation with the variables in there. Moles, always measured in moles. Volume, most often, always when we're doing molar concentration, going to be measured in liters. So this is an equation, but you don't have to use it as an equation. Again, best way to do things is with conversion factors, and then you will never make a mistake. For example, what is the molar concentration of a 250 ml solution that contains 29.2 grams of sodium chloride? So we've got a certain mass of sodium chloride, we're going to put it into a certain volume of solution, and we want to know what the molar concentration is. Now, we can't just take mass and divide by milliliters, because we're not interested in a mass volume percentage. We want to know molar concentration. So we have to take our mass and we have to convert that to moles. And then we'll divided by liters, and we'll have it as a concentration. So to convert to moles, we take our mass, we can take a conversion factor, and again, calculate the molar mass of sodium chloride. We use that as a conversion factor to convert our mass into moles. Units of grams will cancel out, and our answer will be in moles. Now, I'm keeping one extra sig dig here. I'm going in my calculation with 4 sig digs, so I'm going to keep one extra one throughout the calculation and fix that up at the end. So I know that when I have 29.22 grams of sodium chloride, I actually have 0.50000 moles of sodium chloride. I can use that then with the volume to find the concentration. So that's my moles. I can then take my moles, and remember I want my answer to be in moles per liter. That is the unit I will be using when I'm expressing my answer in molar concentration. I already have moles, so I don't want to get rid of moles. I just want to have liters as well. So all I have to do is take my number of moles and divide by the number of liters. You can do that. You could just take this and say, okay, I'm going to divide by however many liters I have. You can convert milliliters to liters. That would work. But again, if you use a conversion factor, this one's a little bit tricky if you're not completely comfortable with fractions. But if you think about it, if I'm dividing by my volume, which is 0.250 liters, 250 milliliters is 0.250 liters. So I could divide by 0.250, that's fine. But I could also use it as a conversion factor. If I multiply by 1 over that number, 0.25 liters, that's the same thing as dividing by 0.25 liters. This way I have a consistent setup with my conversion factors, and I would get my answer in moles per liter. So I end up with my answer in 2 moles per liter. Now, this is the slower way of doing it, where you do each step, you write out the answer, you use that answer, and use it in the next step. Quicker way of doing it, as I have down here, quickly we can take the same mass, we can apply the first conversion factor that'll get us to moles. We don't need to write out what the moles is. We can just apply the second conversion factor, which is taking our liters, and again, another reason why you might want to not divide it by it, but instead multiply by 1 over 0.25 liters. And grams cancels out in the first calculation. The moles carries through to the end, the liters carries through on the denominator to the end, and I get same answer, obviously 2.00 moles per liter of sodium chloride. Here the moles, units of moles carry through as a numerator, units of liters carries through as a denominator,